Good day everyone, we are the Spark Plug group. Our mother is Lenny Robredo and she has two sons, Jason Gagnon and Gerald Atras taking the BSME.
Part 1, Chapter 1, Mathematical Modeling, Numerical Methods, and Problem Solving. First, we have a simple mathematical model. A mathematical model can be broadly defined as a formulation or equation that expresses the essential features of a physical system or process in a mathematical terms. Models can be represented by a functional relationship between dependent variables, independent variables, parameters, and forcing functions. As you can see in model function, dependent variable is a characteristic that usually reflects the behavior or state of the system, and the independent variables, dimensions such as time and space along which the system's behavior is being determined. The parameters, constant reflective of the system's properties or composition, unless forcing functions is the external influences acting upon the system. We have here a model function example. Assuming a bungee jumper is in mid-flight, an analytical model for jumper's velocity accounting for drag is v times t is equal to the square root of gm over cd tan h times the square root of gcd over m times t, where dependent variable velocity v and the independent variables is the time t. Parameters is the mass m, drag coefficient cd, and lastly the forcing function is the gravitational acceleration g. A is equal to f over m, where a is the dependent variable, f is the forcing function, and m is the parameter. In the numerical modeling, some system models can be given as implicit functions or as differential equations. This can be solved either using analytical methods or numerical methods. The example, the bungee jumper velocity equation is the dv over dt is equal to g minus cd over m v squared, where analytical solution cannot be obtained using simple algebraic manipulation. It is because velocity is expressed as a differential equation. The MATLAB environment. MATLAB uses three primary windows. The command window, used to enter commands and data, and the graphics windows, used to display plots and graphics. The edit window, used to create and edit M files, programs, example, program m.m. Depending on your computer platform and the version of MATLAB used, these windows may have different looks and feels. The calculator mode. The MATLAB command window can use as a calculator where you can type in commands line by line. Whenever a calculation is performed, MATLAB will assign the result to built-in variables answer. We have here example, we command 55 minus 16. The MATLAB will display the result. The answer is equal to 39. And we command answer plus 11, it will equal to 50. Notice that MATLAB has automatically assigned the answer to a variable. Thus, you could now use the answer as a subsequent calculation. where answer the value of answer is 39. MATLAB assigns the result to the answer whenever you do not explicitly assign the calculation to a variable of your own choosing. Assignment scholars. To assign a single value to a variable, simply type the variable name, the equal sign, and the value. We command a equal to 4. Note that variable names must start with a letter, though they can contain letters, numbers, and the underscore symbol. We will proceed to arrays, vectors, and matrices. MATLAB can automatically handle rectangular arrays of data. One-dimensional arrays are called vectors, and two-dimensional are called matrices. Matrices are set of using square brackets. Entries within a row are separated by spaces or commas. Rows are separated by semicolons. And now, we will proceed to Part 1, Chapter 3, Programming with MATLAB. First, mfiles. While commands can be entered directly to the command window, MATLAB also allows you to put commands in the text files called mfiles. Mfiles are so named because the files are stored with a .m extension. There are two main kinds of mfile: script files and function files. First, script files. A script file is merely a set of MATLAB commands that are saved on a file. When MATLAB runs a script file, it is as if you type the character stored in the file in the command window. Scripts can be executed either by typing their name in the command window by selecting the debug, run, or save and run command in the editing window. Second is the function files. Function files serve an entirely different purpose from script files. Function files can accept input, arguments from, and return outputs to the command window, but variables created and manipulated within the function do not impact the command window. Function file syntax. The general syntax for function is function outvar is equal to function name. And as you can see here, outvar is equal to value where outvar output variable name, func name is the function's name, arglist input argument list, comma delimited list of what the function calls, values passed to it. Help comments, text to show with help function name. The statement, MATLAB commands for the function. Subfunctions. A function file can contain a single function, but it can also contain a primary function and one or more subfunctions. The primary function is whatever function is listed first in the M file. Its function name should be the same as the file name. The subfunctions are listed below the primary function. Note that they are only accessible by the main function and subfunctions within the same M file and not by the command window or any other function or scripts. Structured programming. Structured programming allows MATLAB to make decisions or selections based on conditions of the program. Decisions. Decisions are made in MATLAB using if structures, which may also include several else-if branches and possibly a catch-all else branch. Deciding which branch runs is based on the result of conditions which are either true or false. If an tree F3 hits a true condition, that branch and that branch only runs, then the tree terminates. If an tree F3 gets to an else statement without running any prior branch, that branch will run. Note, if the condition is a matrix, it is considered true if and only if all entries are true or non-zero. Selections. Selections are made in MATLAB using switch structures, which may also include a catch-all otherwise choice. Deciding which branch runs is based on comparing the value in some test expression with values attached to different cases. If the test expression matches the value attached to a case, that case's branch will run. If no cases match and there is an otherwise statement, that branch will run. Loops. Another programming structure involves loops, where the same lines of code are run several times. There are two types of loop. A for loop ends after a specified number of repetitions established by the number of columns given to an index variable. A while loop ends in the basis of a logical condition. And we will proceed to the last chapter, part 1, chapter 4, round-off and truncation errors. Error. To solve a problem, example bungee jump problem with a computer, we have to approximate the derivative of velocity with a finite difference. As you can see here the formula, the resulting solution is not exact. That is, it has error or deviation from true value, truncation error. Also, the computer is a digital device. The computer is limited and representing the real numbers. The machine itself produces an error and solution, round-off error. And the accuracy and precision. Accuracy refers to how closely a computed or measured value agrees with the true value, while precision refers to how closely individual computed or measured values agree with each other. As you can see here in our illustration, we have A, we have the inaccurate and imprecise, and B, accurate and imprecise, and C, inaccurate and precise, and D, accurate and precise. Accuracy and precision. Inaccuracy, systematic deviation from the true value, and imprecision, the magnitude of the scatter. Numerical method should be sufficiently accurate and precise enough. We have the error definitions. The true error, UT, the difference between the true value and the approximation, where ET is equal to true value minus the approximation. And for the absolute value, the absolute difference between the true value and the approximation. The true fractional relative error through the true error divided by the true value, and the relative error, the true fractional relative error expressed as a percentage, where relative error is equal to true value minus approximation over the true value times 100%. And the round-off errors. Round-off errors arise because digital computers cannot represent some quantities exactly. There are two major facets of round-off errors involved in numerical calculations. Digital computers have size and precision limits on their ability to represent numbers. Certain numerical manipulations are highly sensitive to round-off errors. We have the truncation errors. Truncation errors are those that result from using an approximation in place of an exact mathematical procedure. We have the example 1. Approximation to our derivative using a finite difference equation. You can see here our formula. And then we proceed to the Taylor theorem in series. The Taylor theorem states that any smooth function can be approximated as a polynomial. And the Taylor series provides a means to express this idea mathematically. You have here the Taylor series, see here in the graph. The function value at x is equal to x I plus 1 can be approximated by the information of the function at x equal to x I, which is closed. The truncation error. In general, the nth order Taylor series expansion will be exact for an nth order polynomial. In other cases, the remainder term Rn is of the order of h n plus 1, meaning the more terms are used, the smaller the error, and the smaller the spacing, the smaller the error for a given number of terms. And that's all for part 1. Thank you.
Good day everyone. Gerald De Atras and Jason Gagnon reporting the summarizations of numerical methods for engineers 6 editions. Part 1 and Part 2. Our topics: Introduction of Part 2, bracketing methods, graphical methods, bisection methods, false position, incremental searches. First is the quadratic formula. X is equal to negative b plus minus square root of b squared minus 4ac all over 2a. To solve, f of x is equals to ax squared plus bx plus c equals 0. Root of an equation, value of x that makes f x is equals to 0. Thus, root are sometimes called the zero of an equation. Although the quadratic formula is handy for solving that same type of function, there are many other functions for which the root cannot be determined so easily. For these cases, the numerical methods described in chapter 5, 6, and 7 provide efficient means to obtain the answer. Okay. Non-computer method for determining roots, approximate solution technique. First is the graphical method, plotting the function and determine where it crosses the x-axis, the point which is represent the x value for which fx is equals to 0. And the second is the trial and error. These techniques consist of guessing a value of a x and evaluating whether fx is 0, if not as small always the case. Another guess is made of fx is again evaluated to determine whether the new value provides a better estimate of the root. The process is repeated until a guess is obtained that results in an fx that is close to 0. Standard method for locating roots. The determination of the real roots of algebraic and transcendental equation. These techniques are usually designed to determine the value of a single real root on the basis of foreknowledge of its approximate location. For algebraic function, f sub 2, quantity x is equals to 1 minus 2.37x plus 7.2x squared. And f sub 6, quantity x is equals to 5 squared minus x cubed plus 7x raised to the power of 6. And for the transcendental function is f quantity x is equals to ln x squared minus 1, and f quantity x equals e raised to the power of negative 0.2x sine quantity 3x minus 0.5 quantity. In additional, a transcendental function is one is that non-algebraic. A transcendental function is one that is non-algebraic. This include trigonometric, exponential, logarithmic, and other less familiar functions. The determination of all real and complex roots of polynomials. These methods are specifically designed for polynomials. They systematically determine all the roots of the polynomial rather than determining a single real root given an approximate. Bracketing method deals with methods that exploit the fact that a function typically changes sign in the vicinity of a root. Two initial guesses for the root are required. These guesses must bracket or be either side of the root. Graphical method. Graphical techniques are of limited practical value because they are not precise. Can be utilized to obtain rough estimates of roots. These estimates can be employed as starting guesses for other numerical methods. Are important tools for understanding the properties of the functions and anticipating the pitfalls of the numerical methods. General cases. Figure 5.2. Illustration of a number of general ways that a root may occur in an interval prescribes by a lower bound x sub I and an upper bound x sub u. Parts A and C indicate that if both f(x) and f(x) sub I have the same sign, either there will be no root or there will be an even number of roots within the interval. Parts B and D indicate that if the function has different signs at the endpoints, there will be an odd number of roots in the interval. Exemption to general cases. Figure 5.3. Illustration of some conceptions to the general cases depicted in Figure 5.2. A multiple root that occurs when the function is tangential to the x-axis. For this case, although the endpoints are of opposite sign, there are an even number of axis intersection for the interval. B. Discontinuous function where endpoints of opposite sign bracket an even number of roots. Special strategies are required for determining the roots for these cases. The false position method, an alternative to bisection method, brute force approach, is relatively inefficient, also called linear interpolation method. Pitfall of false position method. Although the false position method would seem to always be bracketing method of preference, there are cases where it performs poorly. One-sidedness, as iterations are proceeding, one of the bracketing points will tend to stay fixed. And we will go to the false position formula. A graphical depiction of the methods of the false position, similar triangles used to derive the formula for the method are shaded. So, in the formula is x sub r equals x sub u minus f quantity x sub u quantity x sub 1 minus x sub u all over f quantity x sub 1 minus f quantity x sub u. Modified false position. One way to mitigate the one-sided nature of false position is to have the algorithm detect when one of the bounds is stuck. If this occurs, the function value at the stagnant bound can be divided in half. Incremental searches and determining initial guesses. Locating an interval where the function changes sign, then the location of a sign change, and consequently the root is identified more precisely by dividing the interval into a number of subintervals. A potential problem with an incremental search is the choice of the increment length. So let's go to the open methods. 6.5 multiple roots and 6.6 system of a nonlinear equation. First is the multiple roots. A multiple roots corresponds to a points where a function is tangent to the x-axis. F, quantity x, is equals to quantity x minus 3, quantity x minus 1, quantity x minus 1, then f, quantity x equals to x cubed minus 5x squared plus 7x minus 3. Then fx is equals to quantity x minus 3, quantity x minus 1, quantity x minus 1, quantity x minus 1. And then f quantity x is equals to x raised to the power of 4 minus x 6x cubed plus 12x squared minus 10x plus 3. Then, above are examples of multiple roots that are tangential to the x-axis. Notice that the function does not cross the x on their sides of even multiple roots a and c, whereas it crosses the axis for odd cases b. Pose some difficulties for many of the numerical methods described in part 2. The fact that the function does not change sign at even multiple roots precludes the use of the reliable bracketing methods that were discussed in chapter 5. Another possible problem is related to the fact that not only f of x but also f prime x goes to 0 at the root. This poses problem for both the Newton-Raphson and second methods, which both contain the derivative or estimate in the denominator their respective formulas. This could not result in division by 0 when the solution of converges very close to the root. A simple way to circumvent this problem is based on the fact that it can be demonstrated theoretically. Ralston and Rabinowitz, 1978, that f(x) will be always reach 0 before f prime x. Therefore, if a zero check for fx is incorporated into computer program, that the computation can be determined before f prime x reaches 0. 3. It can be demonstrated that the Newton-Raphson and second methods are linearly rather than quadratically convergent for multiple roots. Ralston and Rabinowitz in 1978 modification have been proposed to alleviate this problem. Ralston and Rabinowitz in 1978 have indicated that a slight change in the Newton-Raphson's formulation returns into a quadratic convergence, as in x sub I plus 1 equals to x sub I x sub I minus m f quantity x sub I over f prime quantity x sub I, where m is multiplicity of the root, that is m is equals 2 for a double root, m is equals to 3 for a triple root, and etc. Another alternative also suggested by Ralston and Rabinowitz in 1978 is to define a new function, the ux, That is the ratio of the function to its derivative, as in ux is equals to f sub x is equals to fx over f prime x. Then, substituting this to the Newton-Raphson formula to develop an alternative form. X sub I plus 1 is equals to x sub I minus u quantity x sub I over u prime quantity x sub I. Then, differentiate and simplify to yield the modified Newton-Raphson method given by x sub I plus 1 is equals to x sub I minus f quantity x sub I, f prime quantity x sub I over f prime quantity x sub I raised to the power of 2 minus f quantity x sub I f double prime x sub I. The preceding example illustrates that the trade-offs involved in opting for the modified Newton-Raphson method. Although it preferable for multiple roots, it is somewhat less efficient and requires more computational effort than the standard method for simple roots. It should be noted that a modified version of the second method suit for multiple root can also be developed. The resulting formula is Ralston and Rabinowitz in 1978 that x sub I plus 1 is equals to x sub I minus u quantity x sub I minus 1 minus x sub I over u quantity x sub I minus 1 minus u quantity x sub I.